So far in this course, most of our theory and techniques of solving differential equations has relied on the functions involved being continuous. However, for some applications, we may have discontinuous functions involved, so we'll need different techniques for solving such differential equations. The method that we will learn in this class to solve such differential equations is the method of Laplace transforms. Before we define what a Laplace transform is, I want to remind us all that integrals have a smoothing effect on functions. For example, when we differentiate the continuous function y equals the absolute value of x, we get a discontinuous function that's -1 before 0 and 1 after 0. However, if we were to work in reverse, integrating y prime here would smooth out that discontinuity. This smoothing feature of integration will be at the core of why we define a Laplace transform as we do. I also want to note that while the motivation for Laplace transforms is to be able to solve differential equations involving discontinuous functions, it can also be used to solve many differential equations involving continuous functions as well. Before learning how to solve differential equations using Laplace transforms, we first need to define it, as well as bring in some notation. The way that we write a Laplace transform, L of f of t, is as some function f of s, which is defined as the Laplace transform of f of t is the integral from 0 to infinity of e to the negative st times f of t dt. Notice here that the Laplace transform is defined using an improper integral. And since this is an improper integral, f of s is only defined for values of s so that the integral converges. Our first theorem relates to this condition. Suppose that f is a piecewise continuous function, and there exist constants k, a, and m such that f of t is bounded by the absolute value of f of t is less than some exponential function k times e to the at once t reaches a certain value, t greater than or equal to m. Under this condition, the Laplace transform f of s exists for s greater than a. To prove this, we must show that the integral defining f of s converges for s greater than a. We'll start by looking at the integral defined by the Laplace transform, the integral from 0 to infinity of e to the negative st times f of t dt. Since we only know that f of t is bounded by an exponential for t bigger than m, we'll split our integral up from 0 to m and from m to infinity. Since the integral from 0 to m is over a finite range, we know that integral itself is finite, and we don't need to worry about convergence here. For the integral from m to infinity of e to the negative st times f of t dt, we know that f of t is bound by k times e to the at. So this integral is bound by the integral from m to infinity of e to the negative st times k times e to the at dt. Working with this integral, and the fact that for s bigger than a, we have that a minus s is less than 0, we can conclude that the integral from m to infinity of e to the negative st times k e to the at dt can be simplified as k times the integral from m to infinity of e to the a minus st dt, which converges since a minus s is less than 0. So we can conclude that f of s exists for s minus a, as we set out to prove. In the coming videos, we'll compute the Laplace transform of functions that often come up in the differential equations that we study. Once we understand the Laplace transform of several functions, we can begin to look at solving differential equations using these Laplace transforms.